Okay. Hello, everyone. Um, Hello, everyone. So I hope you can see my screen. Hi, Reza. Hi, Reza. Uh, Sorry, Reza. So I thought you can also be part of the video, but I'm not sure how I can enable you to be part of this. Okay, that's fine. First time I'm going live here. Um, so let me just let me know if you can see my this page, and when I'm scrolling up and down, you see it, right? Just let me know. Yes. Okay. Good. Then I can zoom it a little bit, and then we can talk about. Sorry, I don't know how to bring you up. Maybe for next time I'll try to add you somehow. If you have some knowledge about it, just let me know. Just give me some hint. But for now, maybe after I finish this, then if we can, we'll bring you up so that we can discuss about the design. I prepared this document to be more efficient when we are having this live. So this is about designing a search autocomplete system. This system, the most important functionality is that to return, let's say, top most search queries. First, we need to think about the questions that we need to ask to understand the requirements, right? Number one, how many daily active users do we have? Let's assume we have 10 million. Then how many autocomplete suggestion per search we need? It is 5 of them. How to select 5 suggestion? Like, what is the most? It's by popularity from historic query, search query frequencies. What language are supported? Let's think about only English for simplicity. Then do we need to do some spell check, autocorrect supported? Let's say no for now. Capitalization, special character supported? No. Fast response time. So this is kind of non-functional requirement basically, but yeah, search results should show within milliseconds. About the relevance, results should be relevant to the search term, then sorted by popularity and other ranking models. Scalable. This system needs to be scalable. It should be able to handle high traffic volume, especially at peak times. And the system should be highly available, even when part of the system is offline, slow down, or some unexpected error. Still, the main functionality needs to be supported. Uh, okay. Estimates. When it comes to estimates, there are 2 main factors that we want to think of. Basically 3 of them. Bandwidth also is important for some use cases, but here we are going to talk about throughput and storage. Bandwidth is more important for systems when you are uploading, like maybe streaming live or those type of systems. Here, that's not an maybe important factor to think of, but throughput and storage we want to talk about. Um, um, so let's say we have 10 million daily active users, and each user performs 10 searches per day. And each search does have average of 4 words per query, and each word does have 5 character. Then it comes to 20 characters, 20 bytes per query for new search items, right? Then on average, 20 requests are sent to server for each query until the word typing is finished. For example, let's think of the word dinner. Like search, the query is first you type D, then DI, then DIN, and so on. Each of them is gonna be a query, right? A query is sent to back to server. So if you want to calculate the throughput, it's going to be something like this: 10 million, and then 10 million user, 10 queries per day, 20 characters per query. It means 20 queries. Then it'll come up to 2 billion requests per day, which is, if you want to calculate query per second, that will come up to 48K. So if you just do a simple calculation, 2 billion divided by 24 hours, which is like hours in a day, and then the 3,600 seconds per hour, then this is like, and then you also consider the peak hours. Let's say in peak hours, the query will double. So then it's going to be roughly 50K. This is 50K per second, which is a big number, right? So we definitely, our processing needs to be distributed. We need some kind of distributed architecture. One server cannot handle this amount of throughput. Storage. Let's assume 20% of daily queries are new. Then again, with some calculation, we will be adding 0.4 gigabyte of new data per day. And then if you multiply this in 365, which is number of days in a year, and then 10 years, it's going to be terabytes of data. And it's clear that data is also huge, and we need to think about it. And we need basically distributed data stores to store this volume, increasing volume of data. And again, one single database cannot handle it. So we need to distribute the database, not only because of the storage reason, because of throughput also, because the number of query database access cannot be handled by regular databases, out there. So sometimes the reason, when we think about scaling, we should think about a couple of different factors, not just one. We need to think about this throughput, the storage. Sometimes like a storage is enough, one database can serve it, or one server can process the volume and throughput. However, we need to scale for some other reason. For example, some other reason as let's say database can handle the data, but cannot handle the access, database access. So still we need to think of scaling. Or there are some other for geolocation, for example, we need to scale for let's say for availability and for performance, for low latency. These are all different elements that we need to think of, and they most of the time we need to scale because of all these let's say non-functional requirements that we have. So now let's talk about high-level design. Two main services are needed here. One is data gathering, and the other is query service. Data gathering, we need to gather user input queries and aggregate them. probably in real time. Real time processing, though, is expensive, especially for large data sets. And here we are talking about large data sets. We talked about the throughput and the number of new searches per day, even per second. It's a huge number. And real time processing, even though it is um, doable, but it's expensive. It requires some other architecture. In deep dive, we'll talk about it. But here, I think I'm gonna go with batch architecture instead of a real-time processing. We'll talk about it. Then we have query service. Return 5 most frequently searched terms per each search prefix. The data model is going to be something like this, right? We want to search query terms and then their frequencies, and then sort them by frequencies, and get the 5, let's say, most query terms. It's going to be something like this. And then if we think about just a simple table and a query, the query is going to be something like this: select from frequency table where query like this, and then order by frequency, this limit 5. This solution might work for a small data set when a data set is small, but when data grows, accessing database becomes a bottleneck. So we should design for optimization. We should think of some other more practical solution for large volume of data set that we will have. Then deep dive. Let's now deep dive into alternative solution. If this is not a good solution for large data set, what is the alternative? There is We are in this section. We are going to talk about tree in memory data structure for optimization, then explore data gathering and query alternative solutions, and how to scale the database. We know about this tree data structure. That's kind of like a special tree, which we can starts with a root, and then we can have in each layer we can have all let's say alphabetic letters. Then when, let's say, we are searching for the word dinner, this tree can be traced, let's say DFS type, let's say tree traversal, and can find the letter, the word, like more optimized. Like instead of searching the whole data set, it's search like just like log n, which is the height of the tree. And if the length of tree fix is limited to a max length, then this search could be an O1 to find a prefix in a tree. And then for our cases, we normally we save in order not to traverse all the tree path. We can store the words that are being accessed from, let's say, node D in the same node, sorted by their frequencies. Like, let's say, at the node D, dinner has been accessed 20 times, though it has been accessed 15, din has been accessed. So, you get what I mean. So that we don't even have to traverse the whole tree. When we get to the let's say node D, we know where we are at and what is the most frequent access words, search terms from there, so we can autocomplete and show that result, let's say 5 results to the user. Then if we cache top search queries at each node, or want to return top k query terms. In real-time design, this tree needs to be constantly updated and stored in an index frequency table. But this, as you might imagine, this wouldn't be practical to, because it's going to affect search performance. Let's say when we are searching, if we want to update this tree online and then serialize it online in the database and then use it for like to gather the result and send it back, it's not going to be performant. That is why we are proposing an alternative offline data gathering service as below. Let's say for offline data gathering pipeline, we are gonna use analytics logs, our search logs. We should have them somewhere on our servers. Then we can use them. Those are like raw data about search queries, append only, not indexed, just raw data, right? Then uh, as we said, like in previous design, data is updated in real time, but there are two problems over there, right? User enters billions of queries per day. Updating the tree and DB on every query slows down the query service. Then the other thing is that top suggestions may not be changing frequently, right? We don't need to update the tree frequently. Let's say maybe uh, most frequent search items for specific region area is not going to change every second. It's not going to change every, maybe in few hours, maybe even a day, something. So that is why that is why we might not need to do that type of real time analytics, which is super expensive in our case. So using analytics logs um, and have like a scalable data gathering system would be enough for our case. So we will build the tree structure from analytics and logs services in pipelines such as this. We have analytics logs, then we have aggregators, some which get these logs and aggregate them using maybe MapReduce, Spark, those type of languages, and then like in batch mode. This is not a stream. This is like a batch process. And then I'm not detailing like these aggregator and the aggregator how they might have a couple of components itself. It's a little higher level. However, the aggregation happens and then it stores in a database. Data store somewhere like in terms of query terms, time and frequency. And then we have some updated workers that create tree structure from this data and then serialize it into TreeDB and also push it to a tree cache. So in tree cache, we will have something like this, which is indexed, which is based on the tree structure that we have made, and it's ready to serve our queries. And the query is going to be now when user comes over, this is query service. When user come and does some sort of like search, autocomplete result will populate from the cache, which is based on our historic cache search history, and it is most should be up to date at least for the, let's say we run this, let's say we run this pipeline weekly or daily. So for our historic data for the last day or last week, we are sure that our suggestions are valid and relevant. And then, okay, for this TreeDB, we can use a key store database or document store, such as, let's say, MongoDB, which is a good fit for serialized data. This is like the design that I can think of, but let's talk about some optimization here and there in different levels and layers. Let's say, okay, for query service, we are using a cache for low latency. Low latency is one of the requirements, non-functional requirements that we need to meet. But beside that, we can also, this query service needs fast speed. We can use Ajax for sending, receiving, not to refresh the whole page all the time. Then browser caching is also like, these are like client side optimization. Autocomplete search result may not change for a short time. Good to cache the result, let's say for an hour or so, using max age. Then the other one other optimization that we can have here is for analytics logs. Maybe downsampling helps. That logging all search queries needs a lot of processing power, also storage. So maybe we don't need that amount of data, and we can log only one out of, let's say, n requests. This is called downsampling. Then how to update tree structure. So let's say this is happening. Let's say every day we are running this pipeline, and then these update workers can, like if it wants to update the tree node, it's not, again, practical. It's expensive. It's slow. So instead, it's better to just replace it with a new tree structure instead of updating the old ones. And then filter layer, we use remove. So we can have a filter like maybe somewhere before update workers. We can also, or like this part aggregators has some, before this aggregation we have some other layers. For a filter layer, we should remove hateful, violent, sexually explicit, or dangerous suggestions. Filter layers on top of the tree cache based on some rules. And scale the storage. So when we talk about scaling storage, we are talking about sharding, basically. And we want to see how we want to shard. What are we talking about? We are talking about this data, how we want to shard this data. So basically, we go with key, and we want to, let's say, shard this data in distributed data set. But how we want to go for it? These are like some search words. One way is to go with alphabetic order, let's say A to M in one server, N to Z in another, and else. However, this might end up having uneven distribution, which is the bottleneck. The more smart way is to analyze historic data distribution pattern, also consider the geolocation of our searches and search patterns, and based on that, we do this. In some cases, they use some machine learning algorithms to classify these searches based on different factors, including geolocation, and then it gives you a better idea how to do the sharding. So we will need some shard manager. These are like advanced topics. Or we might want to use some auto scaling features, but auto scaling features is most relevant for app servers, not database servers, because for database servers, it's going to be more like talking about like sharding the database rather than it's going to be more challenging to reshard this in production when we have, because this is a stateful. system, not like app server, which are stateless, and we can auto scale them more easily. Um, then, oh, okay, I just forgot. We can talk about consistent hashing when it comes to sharding the database, and detail about this consistent hashing. You can look it up by yourself. And then to support other languages, we store Unicode characters in Trie nodes. Top search queries are different, as I talked already about this, in different countries. Solution is that we build different tries and store them in different databases, and how to support trending real-time search queries. This is where we didn't this is the route that we didn't talk about. We talked about like more batch processing, but when the data are ever coming as a stream continuously, stream processing requires another set of architecture. For our case, with our requirements, we didn't need that. But let's say for let's say Twitter trend, um, we need this real time processing. Batch processing won't reflect the most up to date trends, because over there that needs to be absolutely real time. All changes, like even in like millisecond, needs to be reflected in the result. So that needs stream processing. They need another set of architecture: Apache Hadoop, MapReduce, Spark streaming, and Apache Kafka, and all those, some of the technologies behind them. I have another video, I think about, I'm talking about add click aggregate. In that video, we talked about stream processing. However, for this design, I think we are done, and I covered everything that I had in mind. Okay, let's